Hello everyone, this video is about the implementation of logistic regression using the Scikit library of Python. Specifically in this video we are going to consider the procedures starting from importing and inspecting the data that we are going to use for modeling and pre-processing the data, especially labeling the outcome if the outcome is not numerically coded yet, and transforming the input features data. After that we will train the model of interest and evaluate its performance and make predictions, and also validate the model using the cross-validation technique. After that we will consider the penalized versions of logistic regression models, which include ridge logistic regression, Lasso logistic regression, and elastic net logistic regression. And finally we'll consider how to tune the hyperparameters using the grid search algorithm. So a logistic regression model is a classification model that is used to predict a binary outcome variable y based on a certain set of input features x1, x2, let's say up to xp. So here, since the outcome variable takes two values which are usually coded as 0 and 1, instead of modeling the actual value of y, we are going to model the probability of success or the probability of the outcome of interest. And since logistic regression is a type of generalized linear model, the systematic component is the linear predictor, or what we call linear combination of the covariates. And this linear predictor or linear combination of covariates can take any value, including 0, negative, or positive. Therefore, to represent as a probability model, this linear predictor should pass through that of a logistic or sigmoid function. That is, the probability of success is nothing but a function passing through the sigmoid function, and this becomes 1 over 1 plus e to the power of minus times the linear predictor. So for any value of the linear predictor, this sigmoid transformation will yield a value in between 0 and 1 inclusive. Therefore, it is suitable for modeling probability, or to consider it as a probability model. So the probability of success here is a linear function of the covariates. Even if here this probability of success is a linear function of the covariates, it is possible to linearize using different transformations. And the most common way of transforming this probability of success function into something like a linear model is using that of logit transformation or log odds transformation. The logit of the probability of success is nothing but it is the log of the odds of the probability of success. Yes, logit of probability of success equals log of the odds, or odds is nothing but probability of success divided by probability of failure. So using this logit transformation, it can be set with that of the linear predictor. Therefore, here clearly the logit of the probability of success is a linear function of the covariates, but here the probability of success is not a linear function of the covariates. So here we have the odds probability of success over probability of failure. We can solve also for these odds. So the odds of success, which equals probability of success over probability of failure, can be expressed as an exponential function of the linear predictor. So here, for example, if we consider this logit model, W0 is the bias term of this logit model, and the WGS will stand for the weight associated with each input feature. So here, for example, if we consider W1, when x1 increases by 1 unit, the logit of the probability of success will increase by W1. So here clearly the logit of the probability of success is a linear function of the covariates, and the impact of the covariates on the logit of the probability of success is linear, or that's of additive. But when you consider that of the also of successes, it is an exponential function of the covariates. It is non-linear, but it can be easily interpreted. For example, when x increases by 1 unit, the odds of successes will increase by a factor of e to the power of w1. Similarly, when x2 increases by 1 unit, the odds of successes will increase by a factor of e to the power of w2. So here the odds of successes is an exponential function of the covariates. So the impacts or effect of each covariate on the odds of successes is multiplicative. But the effect of each covariate here on the logit of probability of success is additive. But here the probability of success is a linear function of the covariates. So the effect of each covariate on the probability of success depends on specifically the particular value of that covariate. But for this logit model, we can interpret it as an additive effect on the logit model. But for this odds of successes, we can interpret the parameters as a multiplicative effect of an exponential function. And here this linear predictor or linear combination of the covariates is usually called a decision boundary in logistic regression. So if we set it to 0, now if this linear predictor is greater than or equals to 0, we can say that the predictor class is 1. But if it is less than 0, we can say now the predicted class is 0. Or when this linear predictor is greater than or equals to 0, then the sigmoid transformation of the linear predictor will be greater than or equals to 0.5. So that means the predicted class can be taken as 1. And if this linear predictor is less than 0, in that case the sigmoid transformation of the linear predictor will be less than 0.5, or the probability will be less than 0.5. Then in that case the predicted class can be taken as 0. So in logistic regression model, we are going to find the values of these parameters so that its loss function is minimized, which is usually known as cross entropy loss. So the cross entropy loss, or the objective function for optimizing the logistic regression model, is that of this cross entropy loss that can be expressed in this form. So in scikit-learn, by default, an L2 regularization is applied. This L2 regularization is nothing but something similar to what we call ridge regression. Therefore, by default in scikit-learn, the logistic regression model is a ridge logistic regression model. And the implementation of this L2 regularization is here we have the cross entropy loss plus we have a penalty term. This penalty term by default is nothing but L2 regularization. That means the second norm of the weights of the logistic regression model or the logit model. Now this is a penalty, but the regularization parameter is added to that of the cross entropy loss. Here we have C. This C is the regularization parameter, or let's say that's of something similar to the shrinkage effects that we have considered in linear regression. So in the linear regression, the regularization parameter was here, but now in logistic regression, the regularization parameter corresponds to that of the loss function. So C is a hyperparameter or a regularization parameter, something similar to that of the shrinkage effects that we saw in linear regression. So C is nothing but 1 over alpha. Let's consider alpha which is the regularization parameter that we have considered, let's say, in linear regression. So that's a small value of C means more regularization. Here, for example, if C is large, we are going to minimize more on the loss function. So the impact of the penalty will not be that much. So if C is large, there is no more regularization, or the penalty is being lowered. But if C is small, in that case, we are giving more focus in the optimization to that of the penalty term. Then that means we are giving more regularization. So more regularization penalizes large coefficients, because here you have the squaring process. So large coefficients will penalize more than small values. So this larger regularization has actually the effect of making the training accuracy going down, but it may improve that of the test accuracy. But if C is too large, or if the regularization, if C is too small, that means we are more minimizing that of the penalty term, then in that case we are focusing on, let's say, more regularization. Therefore, if the training accuracy goes too much down, that will not be good, even if the test accuracy is improved. And like that of this second norm of the weight parameters, we can also use that of the L1 norm of these weight parameters. So the L1 performs the feature selection procedure because it sets sum of the coefficients to 0. But the L2 regularization, this one, shrinks the coefficients to be smaller and close to that of 0. So the only difference from that of the penalty methods in linear regression is here the penalty parameter is added to, is multiplied with that of the cross entropy loss, or with that of the loss function in general. So a smaller value of C means more regularization, or the penalty is higher. But when C is higher, the penalty is going to lower, or the impact of the penalty will be lowered. So now let's import and inspect the data that we are going to use for illustrating the implementation of this logistic regression model. The data that we are going to consider is TB related mortality data, and for now let's import these pandas, numpy and matplotlib pyplots libraries. Now I have put the data in my GitHub repo, so let's import the data and see what it looks. So here we have ID, sex, age, BMI, Marstat, residence, TB history, complication, comorbidity, smoking, alcohol, HIV, days. So the outcome of interest here is days. So at the bottom it says 626 rows. That means there are 626 observations, and there are 13 columns. That means 13 variables. But of these 13 variables, one is the ID variable, which is an identifier, and the other is the outcome variable. So we can inspect the data. For example, we can call the attribute shape on our data frame. So this provides the dimension of the data, 626 observations and 13 variables. It is also good to check whether there are missing values or not. In case if there are some missing values, we have to consider missing value imputation techniques before trying to fit or train the model of interest. So if I click here, now it shows the number of missing observations corresponding to each variable. ID is 0, and all the variables have a value 0. That means there is no variable with missing observation. And we can also look at that of the data types related to each variable by calling this info method. So for example, it says ID, it's null, the type is int. That means ID is a numeric variable, and sex its objects, age int is numeric, BMI numeric, and all the others are objects. So here we have two types of in general, two types of data types: an object type and the other, let's say, a numeric type, which could be integer, floats, or any other numeric type. So here, for example, sex is object because here the values are entered as female, male, and so on. So sex is a string variable. It is treated as an object in Python. The same is true for that of marital status, residence, up to days. So that's why it says object, object, object. But let's consider ID. ID, it's actually a numeric variable. Then it considers ID as an integer variable. Therefore here, even if ID is a numeric variable, it is not quantitative in nature. We have to be conscious that ID is not a quantitative variable, even if it is treated as a numeric variable here in this Python data object. It's also good to look at the number of unique values, especially if we have a certain discrete quantitative variable, assuming only a few number of unique values. And for those qualitative variables, it is also essential to look at the number of unique values or unique categories. So if I excuse this, for example, it says ID 626 unique values. So the ID is an identifier. We have 626 rows. Therefore, that indicates that ID is completely unique, or it is a unique identifier. When you consider sex, it is 2. In case if it was something like 3, that means there is some problem. We have to correct in such case. For age and BMI, these unique values will not provide that much meaningful information. For marital status, there are 3 categories, and for the others, there are 2 values or 2 categories. We can also describe the numeric variables that are included in our dataset using the method describe. So here, for example, by default, this describe method by default provides the number of observations, mean, standard deviation, minimum, maximum, and the quartile values for all of the numeric variables. But a numeric variable is not necessarily quantitative. Therefore, these summary measures, except that of the count for the ID variable, have no meaning. But for that of age and BMI, since they are quantitative, it's meaningful. But by default, this describe method just provides descriptive statistics for those numeric variables included in the dataset. Now let's start pre-processing the data that we are going to use for training the logistic regression. So first, let's consider that of the outcome variable, or labeling our outcome variable. Here our outcome variable, the values are alive, something like that. So here for days, it's an object. That means the variable is treated as a string variable. So for our analysis, it should be numerically coded. So here we can call and see, for example, the type of this outcome variable. Yes, now the type of this days variable is objects. That means it is treated as a string variable, but we have to numerically code. So for that we can use the map function on this variable of interest. We can call map, then let's say alive to be coded to 0 and died to be coded to 1. In fact, there are automatic methods of outcome variable encoding techniques, but we have to be sure, or we have to clearly identify the outcome of interest to be modeled. So in the outcome label encoding, for example, there is a label encoder method. In that case, the code 1 may be assigned for active, but since we are interested on the died as our outcome of interest, or we are interested in modeling the probability of dying, therefore this should be clearly set as 1 and the other as 0. So I would prefer to use this map function to clearly encode the labels. So I can run this one and check the type. Now it is encoded. The type now becomes int, numeric. This one was originally it was an object. So let's just replace this days variable with this newly coded variable. So I can run this simply and record the data. So now it's 0, 0 and so on. So we have successfully encoded this outcome variable, which was previously a string variable, but now changed into a numeric variable, specifically taking a value 0 and 1. And it is also essential to know the number of observations belonging to each class of the outcome variable. So let's call our variable, and over that let's call the method value counts. So there are 533 non-days and there are 93 days. And we can also obtain the percentage, or we can convert these absolute observations into percentages by adding a normalize equals true in this value counts method. So now the proportion of success is around 15%, and the proportion of failure is around 85%. Then now we have encoded our target variable into a values 0 and 1. So now let's separate the input features and output feature data. So of these total variables, days is our target variable, ID is an identifier. It is not going to be considered as a covariate, or it's not going to be considered as, let's say, any other interest, so this should be removed. So let's first separate the input features data. So we need to call our data, tbdf is our data, and let's call the method drop. Drop which columns? Let's say ID, because we don't want the ID variable to be included as a covariate. This is our target variable. So let me run it. So this is the data frame consisting of only the covariates to be considered in our model. So you can examine, for example, the shape. Therefore this indicates there are 626 observations. Yes, that's correct. And there are 11 covariates, 11 variables here that are going to be considered as input features. And let's separate that of the target variable data. For that, we need to just extract this variable days from our original data frame. So now we have constructed our input features data frame and that's of output feature data. Now once we split or separate the input features and output features data, Next, we need to split the data into train and test sets. As usual, for two different purposes. The train set is going to be used for training the model of interest, and the test set is going to be used to evaluate the performance of the trained model for unseen data or data sets that is not used for training. So here, for example, in the number of, let's say, in the number of outcomes of or number of observations belonging to our target variable, there are 533 in 0 category and 93 in the 1 category, or there are 85% of individuals were alive and around 15% were died. Then in the case where we have a certain class imbalance or unequal proportion of unequal proportions, it is better to consider what we call stratified splitting techniques instead of a completely random split. Actually, for this case, we can use simply a random splitting, but for example, if let's say if the probability of success is less than 5%, when you make the train and test split, there may be the possibility of including, let's say, all the outcomes in the train set or all the outcomes in the test sets. Then in that case, the modeling will not be possible. So in that case, we need to consider what we call stratified split. Actually, for our case, it is sufficient. You have 85 to 15. We can use a completely random split. But in the case if it is too small, especially if it is less than 5%, it is better to utilize that of the stratified split. So for the split method, we need to call the function train test split from a scalar model selection, and we have to supply the input features data, the output features data. In case if there is a large class imbalance like that of 95%, 5%, and so on, it's better to consider stratification or stratified split. So this part is required, stratified by the outcome variable. But for us, it doesn't matter. We can exclude this one. And the test size, let's consider 20% of the observations for the test set and 80% of the observations for the train set. And this random state is for just ease of reproducibility. So let me run it, and here I'm going to obtain the value counts or number of outcomes in the train sets and number of outcomes in the test sets of that's of the zeros and the ones. So let me run it. So in the train sets there are 85% 0 and around 15% 1. In the test sets the same, 85% nearly, 0 and 15% in the 1. If I exclude this one here, for example, let me exclude this part, the stratification split. Now in this case, that means the split is completely random split. It doesn't depend on the distribution of the outcome variable. Now if I run, it's almost the values are the same, 85, 14, 85, 14. And for the test sets, almost the same. So for our case, it doesn't matter, but in the case, if there is a severe or higher class imbalance, like 95%, 5%, it's better to consider stratified splits like this. We have to consider stratifying the train test splits. So now we have obtained the train input features data the test input features data, the train outcome data, and the train test data. Now let's identify the categorical and quantity features in our input features data. Here we have some variables qualitative and other variables quantitative. Since we are going to apply some set of transformation, it is necessary to identify categorical and quantitative input features. So from our input features data, let me select those objects with type object. Those objects with type object are categorical variables. So you have sex, marital status, residence, and so on. And those that are not objects, that are that of the quantitative variables. So the quantitative variables are age and BMI. But as I said before, here, since all the qualitative variables are entered as string variable, I used this function just to identify whether the variables are qualitative or quantitative. But a variable that is not object is not necessarily quantitative. Therefore, we have to confirm every time. Just for example, here sex, yes, it is qualitative. Marital status, qualitative. Residence, TB history, complication, comorbidity, smoking, alcohol, HIV. And specifically here, for the quantitative, age and BMI. So in case, for example, if this ID variable was just included here, in this case, the ID variable would be included like that of a quantitative type of variable. Therefore, we have to manually select the qualitative and quantitative variables, or we have to using this such type of selection, and we have to just confirm whether each variable is actually quantitative or not. So for now we have two variables which are quantitative, and here we have we have 9 qualitative variables or categorical variables, and we have 2 quantitative variables. Then the reason that we identify these qualitative and quantitative variables is because we are going to apply different types of transformations for those categorical covariates and quantitative covariates. So now let's see transforming the train and test input features data. Transforming the train and test input features data. So feature transformation is the process of converting the features to make them suitable for training the machine learning models, and specifically we may use normalization or standardization for quantitative covariates, and we are going to use one-hot encoding for categorical covariates, or we have to consider what you call demi-coding. So regarding the quantitative variables, if we assume that the variables follow a normal distribution, it is assumed to consider standardization as a better method. But if we assume that the variables, these quantitative variables, are not normally distributed, it is better to use normalization. But there is no in general just hard and fast rule to determine whether to use normalization and standardization. Therefore, most of the time it is recommended to try either normalization and standardization, and to select the one that works best for our modeling. So for this purpose, it is necessary to identify the quantitative and categorical variables as we have done here. And the other, sometimes you may find that the feature transformation done before the train test split, but it is generally recommended to conduct feature transformation after splitting the data into train and test split, or into train and test sets. Therefore, this will help to avoid what we call data leakage problems. Therefore, it is better to transform the data that we have after lots of splitting the data into train and test sets. So here in our train input features data, let's see the shape. In the train data, we have 500 observations included, the remaining in the test data, and there are 11 variables. So here, let me consider the test. Yeah, so totally we had 626 observations. Therefore, of this, 500 belong to the train data and 126 to the test data. In most cases, we have the usual 11 coverage. So now we need to use what we call one-hot encoding for transforming those string variables or qualitative variables into a numeric variable using what we call dummy encoding, and we can use either standard scalar for standardization or min-max scalar for normalization of the quantitative variables. So we can standardize the quantity variables alone, and we can make one-hot encoding for the qualitative variables alone. But instead of doing separately, it could be possible to do both this one-hot encoding for those qualitative variables and standardizing for those quantitative variables simultaneously using a pipeline called column transformer. So we need to import this column transformer from sklearn compose. So this transformer, we say just column transformer, then let's give a name encoder, one-hot encoder, and here we set drop equals first to consider the first category of each of the qualitative variable as a base category. And which variables are going to be one-hot encoded? Those categorical variables that we have already identified here. These variables will be one-hot encoded. And similarly, we can use the standard scalar, giving the name scalar for those quantitative covariates. The quantitative covariates are age and BMI. So using this one, we can transform both qualitative and quantitative variables into their required or appropriate form of transformation. So let me run this code. Now this is the column transformer encoder. Let's check the variables which are going to be one-hot encoded are sex, marital status, residence, TB history, complication, comorbidity, smoking, alcohol, and HIV. So yeah, it's correct. And the scalar, we have age and BMI. Here we are going to just normalize them using their mean and standard deviation. So this is just an initialization of our transformer, but we didn't transform the data yet. We can point to here, not fitted. If you are interested, you can look at the documentation. By clicking here, it opens the column transformer documentation. So now first we have to transform the training set data. So transformer is this one. We need to call the method fit transform, and we have to pass the train data frame. Now it is encoded. Originally the data frame was in a pandas data frame. For example, here if I check, this is a pandas data frame in data frame format, and you have some of the variables which take on string values. But when you transform, all the values becomes numeric. Therefore, those qualitative variables are one-hot encoded or dummy encoded, and those quantity variables are standardized. Here, for example, you can get out the names, let's say, using this get features name out. For example, here the first one stands for the sex male, the reference category is female. For marital status we have never married, and here we have the other category. So for marital status, reference categories, reference category for marital status. Once let me check on just the variable trained if mar stats, then let's say dots value counts. Okay. Train df oh sorry, I have to say x train df, not train df. Yeah, here x train df. Okay, yeah, so the reference category for marital status is married, this never married, and other categories are considered in the dummy encoding. So here we have two values, and for that of residence we have urban, the reference categories that's of rural, and so on. History, yes. Complication, yes. Comorbidity, and so on. So therefore these are our variables. If we look at the length or number of transformed features, 12. Originally we had here 11 input features, but here it becomes 12 because marital status has 3 categories. This variable will have 2 variables which are dummy coded. So totally the total number of variables will be in the transformed dataset 12. And for those quantity variables we have mean and standard deviation. We can get the mean, for example, using these 2 line codes. The mean for BMI is for age 33 and for BMI 17, and the standard deviation for age it is 11.9, and for that's of BMI around 3.6. So once we transform the train data using fit transform, for transforming the test data, instead of fit transform, what we are going to use is transform. So here transformer, we need to call the method transform, and we have to pass the train the test data. Therefore, for those quantity variables, for example, in the train, in the test data, the age and BMI variables are going to be standardized using this mean and this standard deviations. Or specifically, in the test data, age is going to be standardized using a mean of 33 and standard deviation of 11.9, and the BMI is going to be standardized using the mean of 17.8 and standard deviation of 3.6. Therefore here we are not going to use fit transform, rather we have to use transform once we fit the transformation on the test data. So we can run this. Now the test data is also transformed. So let's convert just this train and test outcome variables into NumPy array. It is not a transformation, just we are converting the data type. Or first let me show you just here. So original outcomes train data is it is a pandas series, something like this. But when you convert into an NumPy array, now we have converted into an NumPy array. Let me call this variable. Now it becomes an array form, right? Therefore, it is not a transformation. Just here, we are changing the data type from a pandas series format to an NumPy array format. Otherwise, it is not a transformation. What we need to transform is only the input features data. Now we split the data into input features and output features, and these input features and output features data are split into train and test sets, and the train and test sets are also the input features in the train and test sets are also one-hot encoded and standardized. Now we are ready to train our model of interest. So for training, we need to call the method logistic regression. If you click here, so logistic regression. This logistic regression is found in the sklearn.linear model. We have to import the data. And as I said before, by default, the logistic regression model considers L2 regularization, or it is a ridge logistic regression model, not a standard logistic regression model. Here it says penalty by default L2. Therefore, we have an L2 regularization by default in Scikit-learn. So we need to instantiate the model using this, and after that the methods we can call .fit to train our model. This one is just for instantiating the model of interest or creating an object where the trained model is going to be stored. So to train the model, we need to call the method fit and supply the train input features and the train output data. And we can, after fitting, we can call the method score to get that's of the performance of the model, and the default score here for logistic regression is accuracy. So the accuracy or the proportion of correct predictions will be obtained using this score method. And after training the model, we can also make a prediction. Just we can use the method .predict and supply the input features. And by default, this predict input features predicts the predicted class, that is the predicted values as 0 and 1. If we are interested on the probability, we can use the method predicts_proba. This predicts the probabilities associated with the two outcomes of the target variable. And we can also have extract the attributes, the intercept and the weights using intercept underscore and conf underscore. So let's instantiate our model. First we need to call the method logistic regression from the sklearn linear model. So now we have already called this logistic regression class from sklearn linear model. Now let's instantiate our model of interest and assign a name logistic regression, and let's call it here. Now it's something colored like orange. So here if I click on the parameters, now look, penalty says L2. So by default, this logistic regression is not a standard logistic regression model, rather it is a ridge logistic regression model. And here the penalty parameter C is 1 by default. This C is, let's say, 1 over the penalty that we consider in linear regression. So here we have the penalty is L2, C is 1. That means here if I go back to the first topic here, C, it is multiplied with that of the cross entropy loss, and the penalties are known. This is L2 and the value of C, which is a negative value. So here, by default the L2 regularization is applied and C is 1. So let me minimize this, and here if we set penalty equals none, then this will be a standard logistic regression model. Let me run it. If I see here penalty none, C by default it is 1.0 or 1, but as long as the penalty is none, this regularization will not be applied. Even if it is applied, it doesn't have any impact. So this is a standard logistic regression model, but this one by default is the rich regression model. So let's focus on the standard logistic regression model. So let me instantiate again this standard logistic regression model, setting the penalty to none. So it is not fitted yet. To fit that of the instantiated model with the given data, we have to supply the data by calling the method fit. So I can run it. Now it is trained or fitted, so it says fitted. The parameters are the same, the one which are already initialized. So we can get the parameter estimates. Let's get the intercept using the attribute dot intercept. So if I click here, the intercept is minus 5.7. This is the intercept of the logit model. And if I click here for the weights associated with the different covariates, here are the weights. So let's call the feature names from the transformer. So let's say the first one is sex, therefore this is the effect of sex compared to female, or the effect of male compared to female. And the second one, the effect of never married compared to married, and the effect of this other category compared to married, and so on. So for example here, just the logit increases by 0.26 for males compared to females. That's the logit of the probability of success, increases by 0.26 compared for males compared to females. And now we can also evaluate the performance. Now the default metrics in scikit-learn for logistic regression is accuracy, which indicates the proportion of correct predictions. We can recall that the default metrics in scikit-learn for linear regression is R square, or what we call the coefficient of determination. But for logistic regression, it is accuracy, or proportion of correct predictions. So we need to call the method the score and supply the training data. Therefore, this provides the training accuracy. And if we supply the test data, this provides that of the test accuracy. So let me run both. So the train accuracy is 97%, it's good, and the test accuracy is also 96%. So the performance of the model is almost best. And we can make also prediction by supplying either the training input features data or the test input features data. So white red bread, let me give this object name logistic reg. We need to call the method predict, and we need to supply the data. Here it is the input features training data. Therefore the predicted value is the predicted outcome variable for the training data. So I can run it. Now the cluster predicted. Let me call here. These are the predicted classes. So the predict method predicts the class, whether it is class 0 or 1. That means if the probability is greater than 0.5, probability of success is greater than or equals to 0.5, it will be predicted as 1. But if it is less than 0.5, it will be predicted as 0.5. So let me comment this to remove. Similarly, for the test data, we need to supply just here X tests. Otherwise, everything is the same. So now for the test data, the predicted classes are obtained. These are the predicted classes for the test data. But if we are interested on the predicted probabilities, we can use the method predict proba over our trained model. Therefore, here let's apply the of the train input features data. Now the predicted probabilities are obtained. Let's call them here. Now here we have two arrays. This is the predicted probabilities for all the training observations. Let's just observe the first 10 observations. Just the first 10 observations. Now you have two values. This is for the first observation. This is for the second. Therefore, for each observation, there are two predicted values. Therefore, here, the first one stands for the first class, that is the outcome taking the value 0. And this one is the outcome taking the value 1. So by comparing these two, we can determine whether the predicted class is 1 or 0. For example, let me go back here. In the train data, let me recall again this. Let me display the first 10 observations. Okay. Now, in the first, the predicted class is 0. Now let's compare this value with this value. The larger one is this one. Therefore, the predicted class is 0, or let's say index 0. For the second, it is the same, this one. Second, third, fourth, fifth. Let's consider the fifth one. Second, fourth, fifth. 6 point, sorry. Here we have 6.02, 9.9 minus 0.1. Here we have here for the fifth point, the larger value is this one, and here the predicted class is 1. Therefore, the model predicts a probability value for each category of the outcome variable, and the one that has the largest probability is going to be considered as the predicted class. So let me comment this one and enter. And we can obtain also the predicted probabilities for the test data as usual. And the probability predicted for the test data are also, we have also two predicted probabilities for each observation included in the test data. So the one having a larger value is going to be considered as the predicted class. The first one is for the class indexed with 0, and this one the class indexed with, let's say, 1. And another measure in addition to that of the accuracy measure is the ROC curve or score, or what you call receiver operating characteristics. This curve shows how well a model separates the two different classes across different thresholds, or in general it shows the trade-off between true positive rates and false positive rates. So this ROC curve can be obtained from that of a scalar matrix. Let's import ROC curve display and ROC curve and ROC curve score. So this one is for displaying the ROC curve, in a figure, and this ROC curve also can display outputs of the true positive rates and false positive rates with different thresholds, and the ROC AUC score will provide the overall performance score of the ROC curve, or the area under the curve. So in the predict proba, for example, here Logistic reg predicts proba. This is predicting the of the probabilities, right? So here let me run. We have two probabilities for each observation. The first is for the probability of failure, the second for the probability of success. So here, for example, let's extract the second probabilities that stand for success. Let me just run it in any column. So here I'm selecting the probability of success only, 4.62 something, next 1.3, and so on. So here the probability of success is selected. So here let me add this indexing, and I can call it here, which is the probability of success. This has the probability of success for all observations. We have excluded the probability of failure, which is obtained using this predict proba, but we are interested on the probability of success. So for extracting this probability of success, we use this indexing, all observations, but that's of the second, let's say, column that stands for the probability of success. So, and similarly, we can use the probability of success using that of the test data. This has the probability of success for the test data. So the ROC curve displays a tuple consisting of 4 values. Let me show you this ROC curve. We need to supply the actual, let's say, training observations and the predicted probabilities for the training data. Okay, I think I need to run or import this one. So this ROC curve provides a tuple of 4. Let me use test data just for ease of clarity, because the number of observations in the test data are smaller, therefore it is easy to observe. Now we have 4 results which are consisted in a tuple: 1, 2, 3. Therefore the first one is, this one represents the true, that's of the false positive rates, and this one the true positive rates, and these are the different thresholds assumed. So we are going to plot this false positive rates with that of true positive rates. We are interested in comparing these two summaries, false positive rates and that's of true positive rates. So we can run this one. So the true positive rates are saved here. The false positive rates are saved here. the true positive rates are saved here and the train thresholds are saved here. The same is true for the test data. But what we are interested in plotting this false positive rates with true positive rates. And let's see, we have these lines of codes for plotting these false positive rates and true positive rates for both the training and test data sets. Let me run it. Now, here along the x-axis we have the false positive rates, true positive rates along the axis, and false positive rate along the x-axis and true positive rate along the y-axis. So let's consider the train set. Now, that's of the blue line is just a line connecting the intersection points of what? These true positive rates and false positive rates. So it is just higher or it is above this diagonal line, therefore the training performance is well, and the same is true for that of the test performance. If the model is something like a random model, the curve will be something like around here, with the one which is like broken, or let's say a dashed line. So a random model will have a curve something like this. But a model above this is a better model, but a model having a line below this is something like a bad model. That's even cannot perform like that of a random model. So here we have what you call area under the curve. If we have a random model, the line will be like this. So this line covers half of the area. So in that case it could be 50%. Again here we have 50% for a random model. But for our model of interest here, the area below this blue line is much greater than 50%. And specifically the area under this curve is, for example, 0.99. For the test again 0.99. Therefore the performance of the model is better. But if it is a random model, that means the true positive rates and the false positive rates are equal. Then in that case the line could be something like this, a diagonal that passes through this 45-degree line. 45-degree line. So the larger the area under this receiver operating characteristics is, the better the model, especially if it is greater than 0.5. So a randomly guessing model will be correct only 50% of the time. In that case where the true positive rates and the false positive rate are equal. True positive rates and false positive rate are equal. So we can summarize this area. It's also the area under the curve is actually here. It is summarized as 0.99. 0.99. We can also use the function ROC AUC score to summarize this AUC, area under the curve for the training set, and the area under the curve for the test set. So if I run it, now the training area under the curve is 98.5%, and the area under the curve for the testing set is 99%. So it is already shown 0.99, 0.99. Here actually it is 0.985, but here it is considering 2 digits, therefore it becomes 0.99. Actually the actual value of the area under the curve for the training set is 0.985. So the larger the area under the curve, the better the model. The better the model. So here we have considered a single splits, and the training accuracy is 97% and the test accuracy is 96%. It is good, but we have only single splits. And similarly for the area under the curve for the training set, it is 98.5%, and for the test it is 99%. It is good, but this could be by chance. We have to validate the model using cross validation. So for that we need to call the function cross val score from a scalar model selection, and first we have to instantiate our model of interest. Now for now our model of interest is the standard logistic regression model with no penalty. So let's instantiate this model. So it's instantiated penalty none, yeah, because here we have specified as none, and the default metric in the cross validation is actually accuracy. So we need to call the function cross val score the estimator. The estimator in our case is this logistic regression model, which is a standard logistic regression model. Logistic reg. For X we have to supply the training data, and for Y we have to supply the training outcome data. Let the number of cross validations be 10. That means this training data are going to split into 10 different folds. In each fold, one split is going to be considered as a test set, and the other 9 splits are going to be considered as a training sets. And finally, we are going to obtain the scores of the 10 different folds. So let me run it. So here, for example, in the first split, the training accuracy was 96%, in the second 100%, in the third 90%, and in the 10th 94%. So we can obtain the average of these scores and compare with that of the model that is trained with the full training set. So we can use this NP mean to obtain the average. Now it becomes 96.62%. So this is the cross validation accuracy, 96.2, but the one that is trained using the full training set is, here it is, 97%. So 97, 96, there is no much difference, therefore there is no problem of overfitting or there is no problem of underfitting. We can also change the default metric in this cross val score is accuracy, but we can change to ROC AUC if we are interested. So just with the same function, we need to add here an option scoring. Let the scoring be ROC AUC. Everything else is the same as this one. Here by default, we use the matrix accuracy, and here we are going to set into ROC AUC. And let's see. These are the area under the curve values, 94%, 100%, and so on. And let's obtain the mean scores. 97%. What is the area under the curve for the model trained using that of the full training data set? It is 98.5%. 98.5%. So 97.4%. Again, the accuracy, the cross validation area under the curve score, and the model trained with the full training data sets are almost the same. So again, the model performs better, and there is no overfitting problem and there is no underfitting problem as long as the values are close to each other. So far we have considered the of the regular or the standard logistic regression model. Now let's consider that of the penalized versions of logistic regression model. So if I call this logistic regression function, for example, by default it has a penalty L2. Therefore the default logistic regression in scikit-learn is a ridge type of logistic regression model, or a ridge logistic regression. So for the logistic regression model, we just need to call logistic regression as it is, because by default L2 regularization is added. Then after that we can call the method fits to to train this ridge logistic regression model. And after that, we can obtain the score for the training set by supplying the training data, and for the test sets by supplying this test data to obtain the test score. So let me run it. Now for this ridge logistic regression, the training accuracy is 96% and the testing accuracy is 95%. And for that and another things here I need to show to you is here by default it is L2 regularization. So let me see the documentation. Now by default it is L2 regularization, but we can use that of L1 regularization, and also we can use what you call that of the elastic nets method, which considers both the L1 and L2 regularizations. However, here as I said before, regularization is applied by default in the logistic regression model of Scikit, and we can specify none for the standard logistic regression model, and you can add L2 for a ridge logistic regression model, and L1 for a Lasso logistic regression model, and elastic nets to consider the penalty terms associated with ridge and Lasso logistic regression models. And if you go down, for example, here there are different types of optimization solvers. One is called LBFGS, and another liblinear, Newton CG, Newton Kolosky, SEG, and Saga. And here, for example, if we use the solver LBFGS, which is the default one, only L2 regularization and no regularization can be used. But if we try to use L1 regularization, it will not work. Similarly, if we consider the liblinear solver, it considers only L1 and L2 regularization. But if we set the regularization as none, it will not work. The same is true. If we want to use the elastic nets regularization, we have to change the optimizer to Saga. Otherwise, it will not work. Therefore, here the different types of regularizations depend on that of the type of the optimization solver. Therefore, if we want to use elastic nets, we have to change the solver at the same time to Saga. And if we want to use, let's say, standard logistic regression model, the method should be either LBFGS or this one, or this one, or this one, and so on. So the type of regularization here depends on the type of the optimization solver. So for example, in the second, for example, let's use the Lasso logistic regression. The Lasso logistic regression, it is nothing but that of, it uses the penalty L1. But to use penalty L1, we have to use penalty L1, we have to convert the solver to, let's say, liblinear, or we have to convert to Saga. Otherwise, the L1 regularization will not work. So that's why I changed it. By default, it is LBFGS. So to use L1, I changed the solver to Saga. So let's train the model and get the performance. 96%, 94%. So compared to the first one, the test performance decreases for this Lasso regression. So this would be better, or the ridge logistic regression would may be better. And let's consider elastic net logistic regression. To use elastic net logistic regression, we need to convert the solver to, again, Saga. So again, I change it to Saga and penalty elastic nets, and I added the L1 ratio as 1 and fit the training model and get the performance metrics. So the performance metrics for this elastic nets logistic regression model are the same with that of the Lasso logistic regression model. Therefore, of these three, it seems this one, the ridge logistic regression, seems better because it has a higher test score or test performance. So we have these different types of penalties. So let's use hyperparameter tuning using that of the grid search algorithm. So for this purpose, let's import this grid search CV or grid search cross validation from scalar model selection. So here now for example, last time just we have seen to define the grid search. First we need to define the values of the hyperparameters. So we can define something like C, this one, penalty L1, L2, but for example here if I make it elastic net, and if I try to use this grid search CV, it will not work because elastic net L1 and L2 will not work for all the solvers, or the different penalty methods depend on these different types of solvers. So specifying this form will not be appropriate. Rather, we need to specify the different hyperparameters for each type of model. For example, for the standard model, let's say, for that of, let's consider from that of the L1 regularization. For the Lasso regularization, I say here, for example, penalty L1 in one dictionary. C, let it be from e to the power of, no, I mean 10 to the power of minus 5 to 10 to the power of 5. Let's select 10 observations for the regularization parameter. Let the solvers be liblinear and saga. Let's consider L1. It works if the solver is liblinear and if it is only saga, otherwise it will not work. So solver, let's specify these solvers. For that of the regularization parameter, let's consider values from e to the power of minus 5 and e to the power of 5, and let's select only 10 evenly distributed values. The penalty is L1. For L2 regularization, penalty L2, and let's again the regularization parameter take values from 10 to the power of minus 5 to 10 to the power of 5 and select 10 evenly distributed values. But for this L2 regularization, saga works and SAG works, Newton Kolosky works, Newton CG works, and this liblinear and LBFH. Almost for L2, all of the solvers or all the optimization algorithms work. So I have specified them here. And for that of the elastic nets, for elastic nets, the solver should be only saga. So saga. So for C1, let's it be just 10 different values from 10 to the power of minus 5 to 10 to the power of 5. And for that of the L1 ratio, let's consider a linear space from 0 to 1, and let's take only 5 values. And here is the solver saga as usual. So for example, here we have one hyperparameter here. Here we have 10 hyperparameters, and here we have 2. So here we have 1 times 10 times 2. Here we are going to fit 20 models. So let me say here we have 20 models for the first hyperparameter specification. In the second, here we have L2, and here we have 10 hyperparameter values, and here we have 1, 2, 3, 4, 5, 10 times 5, 50 times 1, 50, plus 50 models for the second hyperparameter specification. And for the third, here we have 1, here we have 10, and here we have 5, here we have 1. 10 times 5, 50. So again, for the third, we have plus 50. Therefore, totally 120 models are going to be fitted. Of these 120 models, we are going to select the one that performs better, or the grid search algorithm is going to select the one that performs best. So let's initialize the logistic regression model first to use the grid search algorithm. So this is the initialization. Penalty L2, but it doesn't matter, it is just the initialization. So even if it says L2, it will be replaced by these specifications when the grid search algorithm trains the different models. So we need to call grid search CV. The estimator is our log reg, the one that we have specified here. The parameter grid, the parameter values, the ones that we have specified here. And let the number of cross validations be 5. Since we have 120 models to be fitted, let's make it just 5. So we are going to obtain just the summaries for 5 different folds. So let me run this model. Grid search CV not defined, so that means I didn't run this one. So param values, oh sorry, I didn't run again this, but I ran this instantiation. So let me run. Now here we have initialized the grid search CV. It is initialized. Parameters, no. Here the grid search CV, the parameters is the estimator, it's the logistic regression, this one. And the parameters are here, they are specified here. These parameters are this one actually. And number of cross validations, we have 5. So we have successfully initiated this grid search CV model. Now let's train the grid search CV model. We need to call the method fit and then supply the train and test. The train data. We need to supply the train data only. The test data should be used for evaluating the performance. So the train data is supplied. So it is going to fit 120 different models considering all the different hyperparameter specifications. So the model is, these are the specifications that we have said before. The best estimator is logistic regression model with a regularization value of 0.278 and penalty L1. That means a Lasso logistic regression, and the solver is Saga. The default is LBFGS, but here the optimal one is this one. So we can display the results using this CV results attribute, but the table is somewhat large, 120 rows, because each row corresponds to the different model that is fitted by the grid search algorithm. There are 17 columns or so characteristics, but it is not easy to observe, so let me pass it. Just let's get the best hyperparameter values. That means these are the best hyperparameter values. So we need to call best params in the grid search model. So let me run it. So C is 0.78, and penalty L1, and the solver Saga. And what is the best score, or what is the best accuracy of the model with these hyperparameters? We can call the method best score. It is 0.96. Therefore 96%. It is just the average score of that's of the cross validations. The average score of the different cross validations, or the 5 different folds. So this is the average score of the 5 different folds. Let's get the actual score in the training data and the actual score in the test data. For that, we can consider again this research model, and you can call the method score and pass the training data to obtain the actual training score. This is the actual training score for our training data, but this is the score of the 5 different folds. That means this training data is divided into 5 different folds, and the average score becomes 96%. But for this particular subset, the score is 0.95. Similarly, with this optimal model, we can determine the performance on the test splits, and for this the performance is 96. Therefore, the model with this optimal hyperparameters, the best cross-validation score, or its best cross-validation score is 96%. Its performance on the train splits is 95.8%, and the performance on the test set is 96.0%. Or using this optimal hyperparameters, we can train a new model. Just logreg, logistic regression, solver, we have to no, so solver is Saga. So solver, we have to change here to Saga and see what is the value. 0.78 penalty L1. Yeah, so we need to train on this new model and get the scores. The scores should be the same. Yeah, using that of the research CV algorithm, using the optimal values, the train performance was 95.8. By retraining the model using this optimal hyperparameters, it becomes 0.958. And for the test, it's 96.03. Again, using that of the research internally with those optimal hyperparameters, again it is 0.96. So here in this hyperparameter specification, we only considered those regularized logistic regression models. Let's include that of the standard logistic regression model together with these hyperparameter specifications, and let's compare. So here I added here penalty none. Therefore, this corresponds to the specification of the standard logistic regression model. For the standard logistic regression model, none. We can use LBFGS, this Newton CG, this Newton Kolosky, and this SAG, and this Saga optimizers. So here I specified the optimizers. That means specifically for this model, we are going to train 1 times 4, yeah. Previously, we had 120 possible models. Now, when we include this hyperparameters for the standard logistic regression model, the total number of models are going to be 124. So with this specification, let's instantiate the model, and let's instantiate the research CV, and let's fit the model of interest, and let's get the best hyperparameters. But previously we have only considered those penalized hyperparameters, but now we have included the parameters associated with the standard logistic regression model. So let me run it. It may take some time because it is going to fit 124 models. Yeah, so for the best parameters becomes penalty none. You see, solver LBFGS. That means of the different penalized models, the standard logistic regression model with no penalty has a better performance. But of those penalized models, the one with Saga solver, a penalty value of 0.78 and a penalty of L1 or Lasso logistic regression was performing better, but this model has no better performance compared to the one with the standard logistic regression model or with no penalty. So let's fit this standard logistic regression model. So logistic regression, the optimal solver is LBFGS, which is the default. Penalty, let's say none. Iterations, let's fit the model and get the score. So if I run this, 97% training performance and 96% testing performance. So of all the different penalized logistic regression models with different penalty parameters and with different penalties, including L1, L2, and ElasticNet, the standard logistic regression model performs better for our TB-related mortality data. So this is all about today's video. In the next video, we'll consider the support vector machine and we'll compare its performance with that of this standard logistic regression model. So thank you for watching. See you then.